The Laws of Thermodynamics by Peter Atkins is a comprehensive exploration of the fundamental principles that govern the behavior of energy and matter in the universe. The book delves into the historical context, mathematical foundations, and practical applications of these laws, as well as their implications for various scientific disciplines. Atkins begins by discussing the origins of thermodynamics in the late 18th and early 19th centuries, highlighting the contributions of key figures such as Count Rumford, Sadi Carnot, and James Joule. He then introduces the four fundamental laws of thermodynamics: Zeroth Law, First Law, Second Law, and Third Law. The Zeroth Law of thermodynamics establishes the concept of temperature as a measure of the average kinetic energy of microscopic particles in a substance. Atkins explains that temperature is relative, with no absolute scale, and that it is determined by comparing the temperatures of two bodies in thermal contact. The Zeroth Law also states that if two bodies are in thermal equilibrium with a third body, they are in thermal equilibrium with each other. The first law of thermodynamics, also known as the law of conservation of energy, states that energy can neither be created nor destroyed, but can only be transformed from one form to another. Atkins provides numerous examples to illustrate this principle, including the conversion of chemical energy to thermal energy during combustion, and the conversion of potential energy to kinetic energy during a falling object. The first law also introduces the concept of internal energy, which is the total energy contained within a system. The second law of thermodynamics deals with the tendency of all natural processes to proceed in a direction that increases entropy, a measure of disorder or randomness in a system. Atkins explains that while the second law does not state that entropy always increases, it can remain constant or even decrease in some cases. It does imply that the total entropy of an isolated system always increases over time. The second law has far-reaching implications, including the impossibility of perpetual motion machines and the necessity of dissipation of energy in all natural processes. The third law of thermodynamics, also known as the law of absolute zero, states that as temperature approaches absolute zero, 0 K or 273.15 degrees C, the entropy of a system approaches a minimum value. This law is important because it provides a reference point for measuring the entropy of other systems and allows scientists to calculate the maximum efficiency of processes such as refrigeration and heat engines. Atkins goes on to discuss the application of thermodynamics in various fields, including chemistry, physics, engineering, and biology. In chemistry, thermodynamics is used to predict the spontaneity and direction of chemical reactions, as well as to calculate the equilibrium constants and reaction energies. In physics, thermodynamics provides a framework for understanding the behavior of gases and liquids, and is essential for the study of phase transitions and critical phenomena. In engineering, thermodynamics underpins the design and operation of power plants, refrigeration systems, and other energy conversion devices. Finally, in biology, thermodynamics helps explain the origin and evolution of life, as well as the metabolic processes that occur within living organisms. Throughout the book, Atkins emphasizes the importance of statistical mechanics in developing a more rigorous understanding of thermodynamics. He introduces the concept of probability distributions and explains how they can be used to describe the behavior of large collections of particles, such as gases and liquids. This approach allows scientists to derive precise mathematical relationships between macroscopic properties, such as temperature and pressure, and microscopic properties, such as the velocities and positions of particles. Atkins also discusses the limitations of classical thermodynamics and introduces the concepts of quantum mechanics and statistical mechanics as ways to extend the applicability of thermodynamic principles to the microscopic realm. He explains how these newer theories build upon the foundations laid by classical thermodynamics while addressing some of its shortcomings, such as the failure to describe phase transitions and critical phenomena accurately. In conclusion, The Laws of Thermodynamics by Peter Atkins provides a comprehensive overview of the fundamental principles that govern the behavior of energy and matter in the universe. Through its exploration of the historical context, mathematical foundations, and practical applications of these laws, the book demonstrates the enduring importance and relevance of thermodynamics across a wide range of scientific disciplines. By emphasizing the connections between classical, quantum, and statistical mechanics, Atkins offers readers a deep understanding of the underlying principles that govern the natural world and the processes that shape our universe.